Can we treat points at infinity like ordinary points on a plane? It turns out that this seemingly innocent idea completely changes geometry, so much so that such a plane no longer fits into 3 dimensions. Taking photos is so common today that we almost intuitively understand how perspective works. If we look at a photo of a staircase, we know that its edges are, in reality, either parallel or perpendicular. But in the image, the lines are no longer truly parallel or perpendicular. Instead, lines that run in the same direction appear to converge and meet at a single point, even though in reality they are parallel and never intersect. This point of intersection is what we call a point at infinity. For us, this feels completely natural. But in the early Renaissance, when the first paintings using perspective began to appear, it was a revolutionary discovery. It was even criticized as being inconsistent with earlier artistic traditions. In the Middle Ages, images were symbolic. For example, more important figures were simply drawn larger. Perspective completely changed this way of thinking. In a perspective image, an object can appear small, not because it is unimportant or physically small, but because it is far away. One of the main criticisms of perspective was that it was merely an optical trick rather than a faithful representation of reality. It distorts proportions, changes the sizes of objects, and even makes parallel lines appear to intersect. Moreover, perspective images did not agree with the mathematical description of space at the time, because in geometry, parallel lines do not intersect. Instead of rejecting perspective as an error, mathematicians asked a different question. What if the image is not wrong, but our geometry is incomplete? In this way, the development of painting led to the creation of a new branch of mathematics, projective geometry. Within this framework, the classical plane was extended by adding points at infinity. This gave rise to a property consistent with what we see in perspective images, that any 2 lines intersect, even those that were previously parallel. Moreover, all these points form a single special line, called the line at infinity. A space extended in this way is known as the projective plane. Although adding points at infinity may sound harmless, it actually changes the properties of the plane in a profound way. Without going into deep mathematics just yet, let's take a look at some surprising consequences of this idea. How do we add points at infinity to the plane? Let's look at a simple example. On the plane, we have 2 lines K and L intersecting at a point A. Now imagine rotating the line K clockwise. The intersection point A starts moving to the right, farther and farther away, until we reach the situation where the lines become parallel. At that moment, we say that the point of intersection has moved off to infinity, and this is exactly the kind of point we add to the projective plane, but we could have done it differently. Instead of rotating the line clockwise, we could rotate it in the opposite direction. Then the point A would move to the left, again, towards infinity. Does that mean there are 2 different points at infinity? One on the left and one on the right? No. In the projective plane, we assume that any 2 lines intersect at exactly 1 point. So the point at infinity on the left and the point at infinity on the right are actually the same point. This leads to an interesting consequence. A line becomes closed. You can think of moving along the line in one direction, and after passing through infinity, you return from the other side. This is somewhat similar to what happens on a sphere. On a sphere, lines can be thought of as great circles. If you move along such a circle, you eventually return to your starting point. However, there is a crucial difference. On a sphere, any 2 great circles intersect in 2 points, whereas in the projective plane, they intersect in exactly 1. So the projective plane is not the same as a sphere, even though it may look similar at first glance. There are several models of the projective plane that help us visualize it and better understand its properties. We will focus on one of them. The projective plane can be visualized as a hemisphere, together with its boundary. Take any point A in the plane. Draw a line from A through the center of the hemisphere. Where this line meets the surface, that point is the image of A. In this way, every point in the plane is mapped onto the hemisphere. But what about points at infinity? Points at infinity represent directions. They correspond to lines parallel to the plane. Such lines just touch the hemisphere along its boundary. They touch it in 2 points. But in the projective plane, we treat those 2 points as one. Now, what about lines? Take a line in the plane. Consider the plane that passes through this line, and the center of the hemisphere. Its intersection with the hemisphere is a semicircle, and that semicircle represents the line. Finally, the line at infinity is simply the boundary of the hemisphere. This gives us a concrete way to see the projective plane. Let's see how things behave on the plane. We'll start with something simple. A circular beam of light shining on a wall. When the flashlight is straight, the shadow is a circle, but as we tilt it, the shape stretches and becomes an ellipse. The more we tilt, the longer the ellipse gets. As the ellipse grows, it approaches the horizon and it passes beyond it. The same situation on the projective plane looks like this. We start with a circle. As we begin to stretch it, it gradually turns into a more and more elongated ellipse, moving toward the horizon. At some point, the ellipse touches the horizon, first at a single point. On the projective plane, this is still just an ordinary ellipse passing through a point at infinity. But on the usual plane, that point does not exist. So the curve is no longer closed and becomes a parabola. If we move the ellipse even further, it starts intersecting the horizon at 2 points. Part of the curve disappears and reappears on the other side. From the perspective of the projective plane, it is still a single, continuous ellipse crossing the line at infinity. But on the ordinary plane, we now see 2 separate branches, a hyperbola. The ellipse divides the plane into 2 regions, the interior, shown in yellow, and the exterior, shown in blue. The exterior region has the shape of a strip. Let me stretch the ellipse a bit so this becomes clearer. Since points at infinity are identified, we can glue the edges of this strip together. But there's one more step. We need to twist it. And what do we get? A Möbius strip. This is the famous Möbius strip from Escher's artwork, a surface with only one side. As you can see, the ants can walk across the entire surface without ever crossing an edge. And in fact, the Möbius strip has exactly one boundary. What we've uncovered is something deeper. The projective plane can be built by taking a disk, whose boundary may be, for example, an ellipse, though its exact shape doesn't matter, and attaching it to a Möbius strip. 2 very different objects, but they share one crucial feature. Each of them has exactly one boundary, and along that boundary, they fit perfectly together. But here's the problem. Try to do this in 3-dimensional space, and something goes wrong. The surface is forced to pass through itself. It cannot exist without self-intersections. To truly complete this construction, cleanly, without any collisions, we need a 4th dimension. There is one more property of the projective plane, and it's hard to believe at first. Take any line, and a point on one side of it. If we move the point farther and farther away from the line, eventually it will cross the horizon and reappear on the other side. And yet, its path never actually crosses the line. This means the point has remained on the same side of the line the entire time, and that leads to a completely unexpected conclusion. A line does not divide the plane into 2 regions. But here's the twist. An ellipse does divide the plane into 2 parts, an inside and an outside. A line does not. In the projective plane, the entire surface lies on one side of every line. Now, let's see what happens to curves. Let's return to our light experiment. As we rotate a circular source of light above the plane, we start with a circle. Then gradually, it stretches into longer and longer ellipses, until at one moment it touches the horizon at a single point. On the ordinary plane, this gives us an open conic, a parabola, but in the projective plane, it is still just an ellipse. If we keep going, the curve crosses the horizon. Now it touches infinity in 2 points, and on the ordinary plane, we see a hyperbola. Understanding this idea that a parabola is an ellipse touching infinity at one point, and a hyperbola is an ellipse that has crossed the horizon, gives us a powerful intuition about these curves. One of the first surprising observations is this. Unlike ellipses and hyperbolas, a parabola has only one possible shape. After all, we were continuously deforming the ellipse, producing many different ellipses along the way. We touched infinity only once, and after crossing it, we again get many different hyperbolas. But wait, you might be wondering, how can that be? After all, we know many different parabolas from graphs of quadratic functions, but are they really all different shapes? Let's take one parabola and zoom out. This is what a parabola looks like from far away. It may feel a bit underwhelming, but remember, a parabola is an ellipse stretched all the way to infinity. Now let's zoom back in. Whether you look at it from far away or up close, it may appear different, but it's still the same curve. That's why different parabolas appear to have different shapes, because we're simply viewing them at different scales. In reality, they are all the same shape. What about tangents at points at infinity? For a parabola, the tangent at its point at infinity is the line at infinity itself, which means, on the ordinary plane, this tangent is simply not visible. For a hyperbola, the situation is different. It has 2 points at infinity, and the tangents at those points do appear on the ordinary plane. They are exactly the 2 asymptotes of the hyperbola. And now, it becomes clear why a hyperbola has asymptotes and a parabola doesn't. By thinking of a parabola as a special case of an ellipse, we can start to see that some of its properties have counterparts in the ellipse, even if they are not projective and depend on angles and distances. An ellipse has a beautiful optical property. A ray coming from one focus reflects off the ellipse and passes through the other focus. Now, a parabola can be seen as what an ellipse becomes when one of its foci moves to infinity. And this is exactly the moment when the ellipse touches infinity. One of the foci is no longer a point. It becomes a direction. And this gives us the familiar optical property of the parabola. Parallel rays reflect and meet at a single point, the focus. We've seen how adding points at infinity changes the nature of the plane. We learned how to split the projective plane into a Möbius strip and a disk. We discovered something surprising about lines. They don't actually divide the projective plane. And we observed what happens to an ellipse when it touches or crosses the line at infinity. That's quite a lot for a short video. Now we should have a pretty good intuition for what infinity means in the projective plane. If you're tired of thinking about perspective, about how all parallel lines seem to meet at the horizon, take a walk in the forest. Find a winding path. Somewhere the horizon disappears and no lines seem to converge. But remember, don't look up. Thank you for watching.